Thanks, Sergey, and thanks to the organizers for setting up this workshop. So today I'm gonna talk to you about the work that we put out in summer, and it's about kinetic theory, so a slightly different topic. I try to be pedagogical. I know that maybe some of you haven't worked in kinetic theory or haven't even heard about kinetic theory. And this work was done in collaboration with two PhD students, one from Wrocław, Rajesh Biswas, and one from Dresden, Paweł Matus, and my colleague, who is also here, Francesco Peña Benitez. So first of all, let me explain that frame-indifferent is basically what in modern terms we would call covariant. So the frame-indifferent is something that, let's say, old practitioners of like kinetic theory and continued mechanics used to call covariant theories. Okay, so just to embed this in the perspective of effective field theories, we all know that there is always an underlying quantum field theory that we like, but sometimes it's difficult to solve. So we come up with all these effective description. One of them, as we heard in the previous talk, is hydrodynamics. So that's the effective theory that happens if the system is strongly coupled. So then based on symmetries, we can somehow reduce the dynamics to the transport coefficients and some conserved charges at low energies. But somehow, sometimes if the system is weakly coupled, this kinetic theory description, which is like a statistical mechanics description, is a useful complementary tool that helps us understand certain features of our systems that go beyond just this macroscopic hydrodynamic formulation. Now let me just introduce a few systems that are perhaps motivating why we should study this. So in high energy, basically there are experiments in like heavy ions that basically collide to heavy nuclei and then check how the resulting blob of strongly coupled matter collides, evolves, and then we are often interested in like the properties of that system, like transport coefficients and what happens in the evolution. Then, in order to correctly capture all the dynamics, it was suggested that both rotation and speed degrees of freedom are necessary. At the same time, rotating fields and spin kind of vorticity interactions is also important in some of the electron flow experiments in pure materials, and then kinetic theory is like a main tool in these studies. So then developing like a proper understanding of kinetic theory in this regime is also relevant. Finally, there are these series of papers that deal with like topological modes of rotating spheres, basically like planets and stars. And then, because of rotation, somehow like the dynamics gets motivated. In fact, like topology seems to be like strictly tied to precisely this this rotating movement, and the topological invariant are only well defined if some transport coefficients like Hall viscosity are included in the description. Okay, on top of that, there are other systems that we studied, for example, systems with like quantum anomalies, then we more or less understand everything in a covariant fashion in the relativistic setup. But then there are also like non-relativistic or like not Lorentz invariant condensed matter materials like multi-valence semimetals with this nonlinear dispersion relations in some direction. So then it would be interesting to see if all these ideas of like anomalies, let's say, survive in that setup. And by now we kind of have a field theory understanding of that, but somehow the kinetic theory formulation is still like not super well understood. So then let me just mention that there is like a non-covariant formulation of kinetic theory with this anomalous transport coefficient, and basically it boils down to some like Berry phases that we can include in the kinetic prescription, and then we can identify these anomalous transport coefficients as stemming from precisely these Berry phases terms that we include in the single particle dynamics. And there are like associated like experimental kind of signatures of them that are visible in the so-called skin effects that that can be probed in some optical type of responses of these veil materials or other like pure materials. Finally, there is like one technical issue that we kind of spotted in the literature that is basically more than 50 years old. So in Germany, like Ingo Miller in the 1970s spotted that if you use traditional kinetic theory that is not formulated in a covariant way and try to compute responses in a rotating frame, then basically even though you covariantize it in some way, you get two different physical results for basically the same quantity. So he computed like heat transport. And this result basically initiated like a long-lasting debate in the community how this is possible that you get two different results in a covariant kind of approach to kinetic theory. And as a byproduct of what we want to do is basically like resolve this paradox. So the tools that we are going to use are strongly based on geometry. So in the past 10 years or 15 years, people studied different symmetry patterns and different underlying geometric formulations of these symmetry patterns. And by now we know that somehow the parent geometry is the so-called Aristotelian geometry. We heard about this like at the beginning of this conference. And this is a geometry that couples to systems without boosts. Then from this geometry, we can generate either like Lorentz invariant setups that have Lorentz boosts, and then we can also generate other less kind of familiar, let's say, scenarios. One is the so-called Newton-Cartan geometry, and this is basically what gives like a covariant formulation of non-relativistic Galilean invariant systems. So this can be also like obtained from Lorentzian geometry when the speed of light goes to infinity. Other regime that we can also probe is the so-called Carolian geometry. So I think the day before yesterday we had like a a question, what the hell is like Carolean geometry? So this is basically like a geometry that appears if we send the speed of light to to 0. And then there are various like product geometries that we can cool up from the combinations of these things. And for example, these like multi-vale semi-metals belong to the category of these like product geometries. So let me just say that a covariant description of kinetic theory is like relatively well understood in the context of like Lorentzian geometry, and astrophysics people have been using this for a long time. But these other let's say geometric structures are much less understood, and to the extent that there is this like paradox that people have been debating for a long time. So in this talk, the ultimate goal is basically to understand this like Newton-Cartan piece of the kinetic theory. So let me start with relativistic particles and give you some like background how we think of kinetic theory in that setup. So kinetic theory is basically like a statistical ensemble of single particle physics. So we need like many particles. We need like to understand the dynamics and then populate them in some statistical way. So in the relativistic case, if we are interested in a single particle, we can write down an effective field theory for this. And usually this field theory in the Lagrangian formulation is just like the shortest path between 2 points of the trajectory that this particle sweeps in space-time. So then the Lagrangian is just like the square root of the metric coupling like the two derivatives of the position. And then if we compute equations of motion, we'll get like just the geodesic equation that appears, plus there is a constraint that we need to satisfy, and basically that the scalar product of velocities is constant. So this is nice, but in order to do like kinetic theory, we need to go to the Hamiltonian picture, because what kinetic theory is basically like a Hamiltonian evolution of particles plus some collision corrections that capture dissipation. So if we go to the Hamiltonian formulation of a single particle, we get basically a gauge theory that has this reparametrization invariance. So if we just try to compute the Hamiltonian, we get 0, because then we have a freedom to choose the time evolution parameter. So basically it's the constraint that captures the whole time dynamics for us. And this is implemented here by this eta parameter that can be thought of as an Einbein, or some like metric on the word line. And then, as I said, like to construct kinetic theory, so basically the dynamics of the observables in phase space, we use Liouville theorem, which says that the evolution of the non-dissipative part of the evolution preserves the volume of the phase space. And then there is a prescription that tells us that a given function that is defined on phase space evolves according to some operator that is called like Liouville operator. Then what we need and what like people studied is basically like the.
I have a short question. So just to be sure, so you're restricting to spin free?
I'm restricting to what?
To spin zero? Because I mean, if you write the actions you looked at, I mean, you can write particles that have also spin.
Yeah, so for the moment it's like no spin, like
okay.
it's a single particle.
Yeah, okay, thank you.
I mean, at the end here, I'll be like interested in like non-relativistic physics, so spin will not be like that relevant. So I will mostly focus on like
I mean,
rotations.
Because, I mean, if you like to think about it, you can think it as like quadrant orbits of the Galilean group, the particles you presented. And you have an invariant that is a spin in the non-relativistic setup. Very similarly, it even derives as a limit from the spin you have in relativistic setups. So you can also write down particles that have additional degrees of freedom that capture the spin.
Yes, that's true. We haven't done that.
Okay, no, okay, just a comment. Thank you.
So basically then what we want to do, we supplement our position, like space, with the tangent bundle. And this tangent bundle corresponds to like momentum. And what we want is basically some like probabilistic description of both like position and momentum. So then mathematicians constructed precisely those bundles. They constructed like volumes. So here there are like expressions what the volumes are both in the space piece and the momentum piece. So we just use this result, and then we want to like construct a distribution function that, if populated, will give us conserved quantities that correspond to some macroscopic degrees of freedom. So the zeroth moment of the distribution function integrated over momenta is basically like the density of particles in spacetime. Then the higher moments correspond to momenta and or currents and stress energy tensors for a given system. And one caveat that is there, and we should always like keep in mind, that if the system is constrained, then we need to implement that constraint also in the integration over volume. So in the relativistic theory, it's done by just putting like the delta function with this on-shell constraint that basically tells us that we stay on shell throughout the evolution of that like relativistic dynamics. Then like the final piece is to write down the Liouville operator, and this can be done using this geodesic equation, and that gives us a closed form equation for the distribution function that in the non-relativistic case is like the Boltzmann equation. In this case, it's called like a Vlasov equation. And then there is a unique solution of that equation, or at least we can constrain to some extent the solution of that equation. That is basically like a polynomial of momenta that we contract with like the Killing equations that we have in the system, and then we re-express everything usually in terms of conserved charges that are in the system that follow from the Netter theorem. Okay, so far so good. We kind of constructed, let's say, relativistic kinetic theory that in principle is covariant. But now the question is, what happens if we have like non-relativistic systems? And then what we need to do is we need to go to this Newton-Cartan framework that correctly captures the geometric structure of non-relativistic systems. And let me give you some brief introduction to Newton-Cartan geometry. I assume that not everybody is familiar with that. So basically, the starting point can be, let's say, the Galilean transformations plus translations of, let's say, a path of a particle, and then the analog of the transformation matrix that is, or that was the Lorentz matrix in the previous case, is now of this non-symmetric form where we have one in the time direction, we have velocity that is a boost parameter in the setup, and then the A corresponds to a rotation matrix in space. Then we can try to construct matrices that are invariant or that leave the distance invariant in the setup, and then it turns out that the structure is more complicated than in the case of Lorentz geometry. So basically we get two matrices. One is all zeros plus 1 in the t00 direction, and then there is a matrix that is purely spatial. As you can see, all these matrices are non-invertible, and basically sometimes instead of tau mu nu, what people do is they use this decomposition into two vectors tau. So that's all, also something that we're gonna do. Then following the usual prescription of the relativistic dynamics, we would like to have a covariant derivative that we can use in this non-relativistic spacetime. But actually here, that's the point where things get more complicated. So if we impose that there is a derivative, a covariant derivative that leaves tau and h covariantly constant, it turns out that the metric or the connection of that covariant derivative is not completely fixed, but there is a transformation that is allowed, and this transformation is basically called the Milne boost. So it's a geometric generalization of Galilean boost. If we do this, if we construct this geometry with this Milne boost, then in the flat space limit, we'll recover theories with Galilean boost. Then the point is that the Milne boost basically transforms us between different frames in the setup, and these frames can be parameterized by a vector here that is then used to construct vectors and metrics with lower indices, as I indicated there. So that we go to the connection, we try to construct the connection, and then it turns out that there are two problems. So one of them is that either we have non-vanishing torsion in the time direction. So that was, I think, mentioned also in some of the talks on Monday. But we can say, okay, we don't want any torsion, but then still, if we require that, the connection is not fixed, and then we are left with one two-form tensor, which I call F, that is completely unspecified. And I mean, the general kind of logic in this Newton-Cartan business is that we have certain freedom, or we have or things that are not defined like or cannot be fixed appear throughout the construction, and somehow we want to we want to give them some like physical interpretation. So actually, if we say that this two-form field has some like underlying potential, in analogy to, let's say, electrodynamics, we can interpret this M later on that basically is like a U1 symmetry that preserves our, or like forces our mass to be conserved, which is like very natural in Galilean invariant systems. So then we have to live with that. We fix this F to be basically like the gauge field that corresponds to like the mass current, but then we need to go through like similar steps as we did for the relativistic physics and basically try to construct the action, the Hamiltonian dynamics, and basically constraints to see, what is like the analogous prescription for the Newton-Cartan geometry in the kinetic theory. So we do that. We can write down the particle dynamics either by taking C limit from, starting with this relativistic particle, or just purely based on symmetries. We construct the geodesic equations, and then we can compute the corresponding netter charges. So in this case, because is a gauge theory, we need to use this generalized netter theorem, which basically says that the variation of the Lagrangian will be proportional to some like derivative of the time parameter. But okay, this is like relatively well understood, so we can go through the procedure, and then we get the form of these conserved charges that you can see at the bottom. So now, all good, but as I said, there is still like some freedom in this construction, and it turns out that if we have systems at finite temperature, the Newton-Cartan structure is not yet enough to fix everything, and in fact, we need an additional vector, and then we can think what is like the interpretation of this additional vector, and then it turns out that a very natural interpretation can be formulated, and basically we can say that a finite density system basically breaks spontaneously like boost symmetries. So this vector parameterizes us the frame in which our, let's say, finite density system is. As only with this additional like vector, we can construct quantities that are invariant with respect to all the symmetries in the problem. So like various like Milne boosts and also like U1 symmetries that appear. So that's like the key point that we'll exploit in the next slides to kind of construct this kinetic theory. And maybe like a final like side comment that I can make. So how can we see like rotation in like Newton-Cartan spacetimes? So for example, this may also be important if you want to study like these rotating crystals that also were mentioned like in one of the talks. So one idea is that we could take like the Newton-Cartan geometry and just like change coordinates. But then it turns out that it's not enough because then we can compute the vorticity of this configuration, and basically it's it's 0. So then what else can we do? Another thing we can try is basically use this Milne transformation and try to somehow generate like a frame in which vorticity is non-zero. But then it turns out that the word-light elements, only if we do like this Milne transformations, the word-light elements of the fluids are not constant. So the most like natural thing to do is basically do both like the coordinate transformation and this Milne parameter shift, and only then we kind of like recover all that we want from like a rotating system. So when the dust settles, basically things that we need to construct things that are covariant in this setup is this tau vector, then like two metrics, gauge field, and this like thermal U vector that we also like declare to be like Milne invariant. Then, as in the relativistic case, we constrain the distribution function in a covariant matter. We use the charges that we fix using generalized Netter's theorem, and populate the states by integrations and over the distribution functions. So as one example, we computed the transport properties in 2 dimensions of a rotating gas, and the outcome is that there are 2 even transport coefficients, which corresponds to conductivity and viscosity, but on top of that there are 2 odd transport coefficients, so that would be like odd viscosity and odd conductivity that basically stem from the fact that we have this underlying symmetry breaking due to rotation. As you see, if we send the collision parameter to 0, the odd part of the transport remains non-zero. So basically, this agrees with our intuition that odd transport remains non-dissipative and remains there if we don't have any collisions in the system. And this computation was done in the so-called relaxation time approximation. So we basically use some simplified model for the collisions on top of these Hamiltonian evolutions that we constructed using Newton-Cartan geometry. So then, just to close, let me just explain to you what is like the resolution of this like paradox that people have been debating. And basically what like Miller did not realize that this arbitrary like frame that one can use, that is in principle covariant, is actually not Milne invariant. So the only way to have something that is like Milne invariant is basically to use this vector U that I told you is basically where is like the frame of the gas or of the fluid that appears in the construction. And only then, if you construct your derivative expansion, you will get quantities that are both like covariant and invariant with respect to all the symmetries. And then there is no paradox that he basically witnessed. Okay, so let me just close that we can like develop a kinetic theory that is like non-relativistic in a frame-independent or frame-indifferent way. This is a systematic tool to include rotations in the Galilean systems, and this like coupling to geometry as we often witness, like in physics, serves as a kind of guiding principle. And now we can try to take this and apply to like various classes of like non-relativistic systems. Thank you.
Yeah, it's maybe more comment or semi-question. So in the relativistic case, you could put the whole system on a Lorentzian geometry. And I guess that's better understood. But then you can 1/c expand that covariantly, and you should recover your answer. It could be interesting to do the test, whether you can get it from that perspective.
I mean, in principle, yes, but expanding in 1/c is not that straightforward because you have all these like things that are not fixed by the geometry. So maybe if you're like skilled and
you can get Newton-Cartan geometry in that way.
Is what?
Newton-Cartan geometry, you can get it from general relativity by expanding in 1/c.
Yeah, the geometry you can get, but I mean, it's not just like geometry. As I told you, you need like some more arguments to.
Yeah, I think a standard non-relativistic approximation of the gas. Wouldn't that work, you think?
I mean, probably now, because we know what the answer is, you could try to do that. But I mean, we started doing like 1/c expansions, and there were some steps that were like non-obvious, let's say.
Right.
And it was somehow like the easiest like to do it like this way.
Okay. Maybe you can tell me more later. Yeah. Thanks.
So I would say like the new ingredient is that you can now do it on like curved backgrounds, but somehow like in flat space, you can just try to generate them using non-inertial frames, and I think that people did in the past. Yeah, B is this like generalized like rotation. Like vorticity. So NT is just like density and temperature. No, it's just like multiplication.
Yeah. Have you thought about the generalization to the product geometries you mentioned at the beginning?
Mm-hmm. You mean like
like the multi-bile semi-meta with different.
So I would say like for the Carolean geometry, I mean, you can construct hydro, it seems, but somehow if you compute like single particle physics, it seems that the particle just needs to stay in like one place. So I'm not sure if there is like a valid kinetic theory description. I see there is some like comment there.
It's a little different because it's even more obscure if you like, but there are also ways. I mean, it's a little bit more obscure if you like, but you can add a mass, a plus mass, minus mass. and then you have like the center of mass is then still conserved, right? So I mean, on the particle level, you can do in principle classically exactly the same thing as you do with this in the fractal picture, that you take a positive and negative mass and move them together, and then the center of mass is still conserved.
Okay,
so in this sense, okay, I'm just saying there could be a way out. I'm not saying this is simple or anything. I'm just saying, okay.
Yeah, we haven't tried to push it, like, and for like the product geometries, we started like playing with that. I mean, if you just relied purely on the symmetries, it seems that in some cases it's not like so constraining as like Newton-Cartan, but maybe if you know something more about the system, like a Hamiltonian, for example, you can do better. But it's like I guess case by case study.
So what exactly do you mean by product geometries here? Do you mean a product of a Newton-Cartan and a Carolian geometry?
So, for example, like because of this anisotropic dispersion relation, so in multivale, you have a symmetry that is like SO1, 1 in, let's say, one time and one space direction, and then it's like Euclidean in the others.
So you mean where you're okay? So are you aware of this terminology that's called kind of like a string Newton-Cartan or string Carol geometry? Is that where you sort of single out a subspace with, in this case, a Lorentzian symmetry, and then you sort of...
Yeah, maybe it's related, but I haven't like thought much about it.
Okay. All right. Okay. So that's what you want. Okay. Thanks.